Allora, un attimo, io mi metto così. Mi sto andando. Ti dico quando partiamo. Bene, potete partire.
Okay, good morning to everybody, and welcome to this PhD thesis defense by Edoardo Iani. Edoardo, you have half an hour and then questions.
Okay, perfect. Thank you very much. So I'm gonna share my screen. Please let me know if you can see my presentation, full screen mode now.
Yes, thank you, go on.
Okay, so good morning, I'm Edoardo Iani, and today I defend my PhD thesis, the role of star formation in the assembly of brightest cluster galaxies and distant clumpy star-forming sources. Due to the limited amount of time available, in the next 30 minutes, I will present a selection of the main results I obtained from the two projects I've carried on during my 3 years of PhD. The first project is about blue filaments in brightest cluster galaxies. It's a project that I started in Padova under the supervision of Professor Giulio Rodighero and Professor Alberto Franceschini, while the second project is about blue clumps in intermediate high redshift galaxies, and is a project I developed during my 1-year studentship at the ESO headquarters in Munich, where I worked together with Dr. Anita Zanella and Dr. Joël Vernet. Both projects are still ongoing, so after presenting each project, I will briefly discuss what future developments I intend to pursue during part of my postdoc at the Kapteyn Institute of Groningen, where I work together with Professor Carina Caputi. As you can see, the topic of these two projects is very different. So with these two projects, I'm targeting galaxies that have different physical properties, that inhabit different environments and different cosmic epochs. However, it is thanks to all these differences that I've been able to study how star formation proceeds in different stages of galaxy evolution, as well as to study its impact on the formation of galaxy substructures. To make my point clearer, allow me to start by introducing the stellar mass versus star formation rate plane of galaxies. We know that star-forming galaxies at a given redshift display a tight relation between their stellar mass and their star formation rate. And this relation is typically referred to as the main sequence of star-forming galaxies. The existence of the main sequence of star-forming galaxies implies that most of star-forming galaxies are indeed forming stars in a quasi-steady regime rather than stochastic, with the star formation that is sustained on long time scales by the inflow of pristine gas from the circumgalactic medium. In this diagram, in addition to main sequence galaxies, we can also detect the presence of two additional classes of objects, the starburst galaxies and the passive or quiescent galaxies. Now, while the passive quiescent galaxies for a given stellar mass show a lower star formation rate than the one predicted by the main sequence, starburst galaxies display an enhanced star formation activity. Up to date, the existence of these three different classes of objects is mostly interpreted as representative of different galaxy evolutionary stages. In this sense, the position of a galaxy in the stellar mass versus star formation rate plane depends and reflects the galaxy evolutionary stage. Now, many different evolutionary tracks have been proposed to describe how exactly a galaxy evolves in this stellar mass versus star formation rate diagram. However, all different schemes have to take into account two different and opposite trends: the enhancement and the decline of the star formation rate with respect to the main sequence. The main idea is that a rotationally supported star-forming galaxy laying along the main sequence of star-forming galaxies and fed by the inflow of pristine gas from its circumgalactic medium can move off main sequence towards higher star formation rate if the galaxy goes through a violent instability event or as a consequence of major merger. Now, the starburst phase is transient because of the, let's say, natural fading of star formation, as well as the decline, the action, of stellar and possibly AGN feedback. And depending on the strength of these two quenching processes, the representative point of the galaxy can move from the starburst region back towards the main sequence, where it can keep forming stars in a steadily way, as long as the galaxy is fed by this new gas from the circumgalactic medium, or directly move towards the region of passive galaxies. Here, the galaxy evolution ends unless some rejuvenation phenomena take place, bringing new extra gas to the galaxy and triggering once again its star formation activity. So with my two projects, I've targeted two well-distinguished and opposite phases of this galaxy evolution. So with the CLAMS project, I've been able to study low-mass galaxies that have recently undergone violent disk instability, while with the BCG project, I'm targeting mostly very massive and typically passive galaxies that, however, are probably undergoing some rejuvenation phenomena. So let's start with the project on brightest cluster galaxies, and allow me to start just describing what a brightest cluster galaxy is. So brightest cluster galaxies are, or BCGs in short, are the largest, most massive and optically luminous galaxies in the universe. They sit almost at rest at the very bottom of cluster gravitational potential well, if the cluster is dynamically relaxed, and they're close to the peak of the X-ray thermal emission originated by the hydrostatic cooling of the hot intracluster medium that permeates galaxy clusters. Now, from a morphological point of view, these galaxies are typically classified as giant ellipticals or city galaxies, and have old stellar populations and little or no dust and gas content. For this reason, they are a clear example of what a passive galaxy is. However, it has been shown that if these galaxies reside in cool core clusters that are dynamically relaxed clusters, where the intracluster medium at their center is cooling via Bremsstrahlung radiation on a time scale that is much shorter than the Hubble time, then these galaxies can display very peculiar properties, as the presence of blue extended structures and bright emission lines in their spectra. So with this first project, we wanted to understand what is the nature and the origin of these peculiar features. To this aim, we have studied the brightest cluster galaxy inhabiting the Hubble 2667 galaxy cluster. This is a galaxy cluster located in the southern celestial hemisphere at about redshift of 0.23. As you can see, I hope you can see at least from the HST RGB cutout on the left-hand side, the brightest cluster galaxy inhabiting this galaxy cluster is indeed showing the presence of blue structures, extended structures, as well as extended and bright emission lines. For this galaxy, we have gathered a multi-wavelength dataset that goes from the X-rays down to the radio domain. The analysis of this multi-wavelength dataset is still partially ongoing. We have recently acquired new ALMA observations for our target. So in the following, I will mostly focus on the results that I've published in my 2019 paper and are based on the optical dataset, so mostly on HST and MUSE, integral field spectroscopy. So what we have found so far for this galaxy is that, well, as expected for brightest cluster galaxy, our target is a massive giant elliptical, and thanks to the modeling, the two-dimensional modeling of its surface brightness profile, we were able to highlight the structure and the extent of these blue components. So as you can see here, indeed, these blue structures constitute an extended and clumpy filament that extends from the very center of the galaxy outwards, up to roughly 15 physical kiloparsecs. So we wanted to investigate what is the nature and the components of this filament. So the first thing we did was to study the stellar kinematic of our galaxy. Here on the left-hand side panel, I'm showing on the left a map for the stellar velocity, on the right-hand side a map for the stellar velocity dispersion. Both maps were obtained from Mu's integral field spectroscopy. And as you can see, our BCG is clearly a dispersion supported system. There is no coherent kinematic pattern as expected for giant ellipticals. However, if you focus your attention on the region where we detect the clumps and the filament, you can see that stars appear to be consistently redshifted of about 100 kilometers per second. And this is already suggesting that our structure, blue structures, is indeed made, but it's partially made of stars. And because of its color, maybe we're looking at a rather young stellar population. But what can we say about the gas component? So we studied the ionized gas, of course. The thing we can do with Mu's observation is in the rest frame optical of the galaxy. And what we did here, because of the wide variety in the emission lines shape within the Mu's data cube, what we did was to look at different velocity channels and found that in general, the gas component shows two different velocities. So we have two different gas components. One that is blue shifted of about 100 kilometers per second with respect to the galaxy systemic velocity. And its emission is rather concentrated towards the innermost region of the galaxy. While there is a second component, a redshifted one, with a similar velocity shift as the stellar component of about 100 kilometers per second again, that this time extends from the very center of the galaxy outwards along the filament. So we want to now try to understand and probe which kind of mechanism is here ionizing the gas, the ISM. Before introducing what we have done, allow me just to say that from our multi-wavelength data set, we know that our galaxy is hosting an AGN. So it's a radio loud source that from X-ray data, we know that the AGN, it hosts an AGN, a type 2 AGN. And also our findings are partially confirmed by, I would say it's more a sanity check in a certain sense, but from the spectral energy distribution fitting we have performed on the photometry, we have, say, gathered together from the UV down to the radio domain, in which you can maybe see that if we want to nicely model the near infrared and mid infrared emission of our galaxy, we need to take into account also for dust emission from the AGN torus. So, however, to distinguish between all the mechanisms, we decided to construct, based on optical UV lines, and empirical diagnostic diagrams. Here I'm showing you on the top panel a typical BPT diagram. Actually, we constructed two additional more BPT-like diagrams, and all the results were consistent with each other. And specifically, we constructed specially resolved BPT diagrams. So here in the panel, you can see a huge variety of crosses. Each cross is the estimate of line ratios from one single Muse spectrum, and it is color-coded according to the distance of the region probed by the spectrum from the galaxy center. So as you can see, while in the innermost region of the galaxy, the emission is likely due to ionization from AGN feedback and AGN line-alike, so AGN type 2. Moving along the filament outwards, we obtain that the mechanism is more composite. So we can have both the contribution of star formation on one side and AGN. So our conclusion is that what we observe with the blue structures are indeed tracing a blue filamentary and clumpy structures that is made of stars and gas, and in particular within which star formation is taking place. But how is it possible that we detect star formation activity within a brightest cluster galaxy? So let's say the answer is rather complex, but one way to look at the problem in a very simple way is that starting again from the idea that we're dealing with a galaxy that inhabits a cool core cluster. So we know that Hubble 2667 is a cool core cluster. This means that the intracluster medium at its center is, let's say, cooling down via Bremsstrahlung radiation. And as a consequence of this cooling down, we have the formation of some subsonic pressure-driven cold flows that moving along the galaxy cluster potential well refuels the central galaxy of gas. The chaotical accretion model tells us that this process of accretion can take place in a stochastic way through the formation of clumps of cold gas. And within these clumps, the condition for the ignition of star formation activity can take place. So with this model, we are able to understand why we have the formation of a filament and why it is star forming. Now, if this filament is able to bring gas towards the very center of the galaxy, and this gas accretes onto the galaxy's supermassive black hole, then this can give rise to AGN feedback. And this gives a complete explanation, I would say, of our findings. So here there is a very brief summary on what we have obtained so far. Allow me to say that as future steps of this work, we want, of course, to conclude the analysis of our multi-wavelength dataset that, as I said, is still ongoing. But of course, we want to extend our analysis to a wider sample, well, a statistical sample of line-emitting BCGs. We already have in our hand data from MUSE and HST for 4 additional galaxies. We would like to extend to an even further number of galaxies, this kind of analysis. But now let's move to the second project, the project concerning blue clumps in intermediate high redshift galaxies, and allow me just to spend a few words on the general context of this project. So roughly 20 years ago, the first in-depth surveys in both optical and near-infrared revealed that galaxies at the cosmic noon often display an irregular morphology that is dominated by bright light concentrations, the so-called clumps. Now, the detection of these clumps arose several questions, many of which are still unsettled, and one for all, the questions regarding clumps' nature. Indeed, while some researchers believe that clumps are just the consequence of UV light leaking through patchy dust distribution within galaxies, as it can be often seen in very heavily obscured objects, others support the hypothesis that clumps are indeed real physical structures, giant star-forming regions that have sizes up to kiloparsec scales and masses on the order of 10 to the 8, 10 to the 9 solar masses. Now, if this last scenario can be considered as true, then we can ask ourselves a few additional questions, among which a very interesting one is the one concerning clumps' fate. And this is interesting because of its possible implications on galaxy evolution. Indeed, numerical simulations have shown that if clumps can survive to star formation feedback for more than 100 million years, they're likely to migrate inwards within the galaxy disk because of dynamical friction and torques, and coalesce at the very center of galaxies, where they can contribute to the formation of a galaxy bulge. Now, the contribution to the buildup of a galaxy bulge really depends on the stellar feedback recipes that are adopted in simulations, and in particular depend on clumps being long-living structures. So the aim of our project is to possibly give an answer to both these questions. We want to understand if indeed we can probe and state that clumps are real physical structures, and we also want to see if we can give some observational constraints, to their lifetime, so to discriminate between these two possible scenarios. To this aim, we have studied a triply imaged lensed clumpy galaxy at a redshift about 3.4. It is lensed by the foreground galaxy cluster Hubble 2895. And for this galaxy, we have gathered a multi-wavelength data set that is made of observations from state-of-the-art facilities. So we have our data set allows us to probe the galaxy rest frame UV, optical, and far-infrared emission. For the UV, we have HST imaging, unfortunately one single passband, and integral field spectroscopy from MUSE. For the optical, we have archive Symphony K band data. And finally, for the far infrared, we have brand new observations from ALMA band 8. Now, the first thing we performed was to probe the galaxy morphology. As I said, and you can see it also by eye, our galaxy is clumpy, but we want, of course, to have a more quantitative estimate on this. So we modeled the two-dimensional surface brightness profile of our galaxy, and found that the UV continuum is likely composed of 4 unresolved clumps that emit roughly 60% of the total galaxy UV emission, and a diffuse component that accounts for the remaining 40%. Now, the HST PSF gives us an intrinsic upper limit on the size of the clumps that is of about 280 parsecs. This value is corrected for magnification. And if we take into account recent findings by Cave and collaborators 2018, we can associate to this clump size an upper limit on their stellar mass that is of about 2 × 10⁸ solar masses. And here I would like to draw your attention on these two values, because according to what our estimates, our clumps are representative of the low mass end of clumps mass distribution. And this is something to bear in mind for the interpretation of the forthcoming results. Now, unfortunately, Muse and Symphony have a coarser spatial resolution than HST, so we were not able to extract the spectra of each single clump. What we did was to extract the integrated spectrum of our galaxy in both optical and UV. So here you can see a zoom-in version of both spectra. For the UV, you can see that we nicely detect the UV stellar continuum, as well as a wide set of emission and absorption lines from the ISM. We go from Lyman alpha down to the carbon-3 doublet, while for the optical, we detect the H beta and the oxygen-3 doublet only. However, this is a very rich set of observables that allows us to infer numerous properties of our galaxy. In the following, I will mostly focus on the results we have obtained and that allowed us to give an answer to the question I presented at the beginning of this section. So the first thing we wanted to check was the mechanism, once again, that is ionizing the ISM in this galaxy. So we constructed an empirical diagnostic diagram, this time based on UV lines, and that we took from Nakajima and collaborators to 2018. And I hope you can see it from the right-hand side panel, but the representative point of our galaxy, the magenta square rectangle, securely locates our galaxy in the region of star-forming sources. So we can exclude the presence, for example, of an AGN. And this is also confirmed by the rather narrow width of the emission lines that is below 200 kilometers per second, as well as the fact that we do not detect other typical features of AGN UV spectra, such as the nitrogen 5 and carbon 4 emission lines. Then, of course, if we want to give an answer to the first question, the question concerning clumps nature, we want to check the dust content of our galaxy. And to do so, leveraging on a UV dataset, the only thing we can do is to look at the UV continuum. So we fitted it with a power law following Calzetti et al. 1991. I found a beta parameter of about -2.5. This means that we are dealing with a UV continuum that is rather steep towards the blue. Now, we know there is no AGN contamination, so this rather steep UV continuum is possibly due to the presence of a young and unobscure stellar population. Indeed, if we convert the beta parameter into extinction, we obtain an EB minus P that is almost consistent with 0. These results are also corroborated by our findings, our analysis of ALMA observations. Here on the top right panel, I'm showing on top of the HST UV image of our galaxy, the contours at 2 and 3 sigma from ALMA, from the dust continuum emission, and you can see that we barely detect the presence of dust. So we're not dealing with a heavily obscure object. So we can say, I would say, rather safely exclude the hypothesis that we are dealing with clumps that are just the consequence of UV light leaking through a patchy and inhomogeneous dust distribution, and really believe that they're giant star-forming regions. So now that we know that our clumps are star-forming regions, we can try to give an estimate on their lifetimes. And to obtain the lifetime, we started from a simple equation, the ratio between the gas mass that is locked within the clumps and the gas mass outflow rate. So the rate at which this gas mass is expelled from the clumps as a consequence of star formation feedback. For the gas mass, we obtain its values from applying the Schmidt-Kennicutt relation and specifically assuming that our clumps are forming stars in a star bursting mode. And this is let's say, supported by recent findings in the literature, in particular from works targeting young clumps. For the m dot parameter, we started from an equation by Pettini et al. 2000, in which m dot is given as the product of several terms, a term that depends on the geometry of the outflow, depends on the neutral hydrogen column density, as well as the expansion velocity that we obtain modeling the Lyman alpha emission, and finally from an x parameter that represents the percentage of atomic hydrogen within the outflowing medium. We do not have any constraint on these x parameters. What we were able to do was to construct some tracks that show us how the lifetime of clumps on the y-axis varies as a function of the x parameter. Here, the three different curves are color-coded according to a different geometry for the outflow. I'm also reporting value by literature, in particular from Zanella et al. 2019, working where the authors found that for clumps having a stellar mass of about 10 to the 9 solar masses, so almost 1 order of magnitude higher than our clumps, the average lifetime of clumps is about 150 million years. As I said, we do not have any constraint on the value of the x parameter. So what we can do is just to look at the general trend of these tracks. And we can see that for most of the tracks, for most of the values, our clumps have lifetimes that are shorter than 100 million years. So this means that our clumps are short-living structures. And this kind of makes sense with our findings on the size and stellar mass content of our clumps. Indeed, their gravitational potential is not deep, is not strong enough to retain much of the outflowing material that expands into the galaxy ISM. So here, a very short summary of this project. What we have found so far, we have studied a triply imaged lens clumpy galaxy at a redshift of about 3.4, and we have found that it hosts 4 unresolved clumps that have sizes below 280 parsecs and masses below 2 × 10⁸ solar masses. So we have clumps that are probing the, low mass end of clumps mass distribution. We know that our galaxy is star forming and thus poor, and this tells us that probably the clumps are indeed giant star forming regions and not just a consequence of UV light leaking through Apache dust distribution, and that clumps, low mass clumps, are likely to be just short-living structures within the galaxy disk. Future developments of this project is to, well, we are already in contact with people at the Max Planck Institute in Munich to create some ad hoc simulations for our target to see under which kind of conditions we are able to form the clumps, if indeed they're short-living, and if so, under which stellar feedback recipes, and what is their impact on the host galaxy. And of course, as in the other case, in the other project, we want to extend our analysis, our methodology to a statistical sample of clumpy galaxies. Of course, this will be a bit challenging because it's a not easy task to, let's say, gather multi-wavelength data set, taking into account Muse observations, ALMA observations for a statistical sample of sources, but we will try to do that as well. So with this, I will conclude my presentation. I thank you for your attention, and I'm ready to take your questions.
Okay, Edoardo, very good, clear presentation. Thanks. So the presentation is open to questions. Who wants to start?
I can start if you want.
Absolutely.
Okay, so in your first cartoon, Edoardo, when you introduce the rejuvenation phenomenon, yes, you show the image of an elliptical turning into a spiral galaxy. Of course, this is not the case of your BCG galaxy. No. And my question is, do you have an idea of the stellar mass, the total stellar mass contributed by this new incoming filament into the total mass of the BCG?
Yeah, the percentage is very small. We were able to reconstruct, let's say, the star formation history of our BCG and different phases through the spectrophotometric fitting codes. So we obtained that it's below, I would say, 1%. So it's a very, very small fraction, as actually I think it's generally expected. And about this, this sketch, it was taken from Carlotta Gruppioni. So it's just to give you a general idea on how exactly could be some galaxy evolution within this stellar mass versus star formation rate plane. But of course, it's not necessarily ad hoc for the single project I have discussed then later on. So.
Yes, of course, I understand. So I also have another question on the second part of your talk. You modeled the light profile, the light contribution of the single patches, the 4 single patches, plus an extended component, diffuse component.
Yes.
So my question is, which kind of fitting function did you use? How many parameters, free parameters you have, and how solid is your fit?
So, well, this is an iterative process that actually has been based kind of on the same methodology applied in a paper by Anita Zanella and collaborators, 2019. So the idea was to first fit one single component just to check which kind of substructures are in the galaxy, define the different clamps, and then fit once again everything together. So the single clamps were fitted with a, let's say, PSF-like function, while for the diffuse component we used a Circic profile. I know that we are dealing with a lensed galaxy, so it's not necessarily true that we are really the Circic profile is the best solution, but actually we obtain very low and non-structural residuals. And at the same time, we also try to verify our estimates applying curve of growth. So we apply a completely different methodology. This time, just looking at how the light increases starting from different apertures and increasing the aperture size. And what we found is a value and values that are absolutely in agreement with what found with the this GAL-fit modeling. So I would say that it's rather robust.
Okay, you are confident about the solution of the light contribution of the single single components, and you said you are exploring the low mass regime for these clamps. So, how typical is this galaxy with respect to the others? I mean,
well, of course, here there is when we talk about clamps in intermediate hierarchy galaxies, it's always a little bit challenging because we are strongly affected by the spatial resolution of the observations we are dealing with, the data set. And so there's a lot of, I would say, debate on that. But in general, yes, when we start to consider clamps that have masses on almost below 10 to the 8, we are actually proving the small size, the low mass sense of clamps mass distribution. Typically, we can be found clamps with masses up to 10 to the 9 or a few 10 to the 9 solar masses. So in a certain sense, they're closer to giant molecular clouds in a way, with values of giant molecular clouds. And this is for sure thanks to the spatial resolution that we can achieve with HST plus lensing effects. So we can really go and probe the properties of our galaxy down to a few hundreds parsecs. But of course, if this galaxy was observed with a different instrument, with a coarser spatial resolution, or it was less strongly lensed, then probably the clamps would have appeared in a different way. So it's, as I said, our estimates are kind of upper limits. It's also true that our clamps that we were detecting could be even smaller. And it's just an effect of the spatial resolution we can achieve up to now.
Okay, thank you.
You're welcome.
Can I ask a question?
Yes, absolutely.
Okay. So Edoardo, very nice talk. Thank you. I have a couple of questions. First on the first part of the presentation and then on the second one. So on the first part of the presentation, you said that this BCG is a radio loud galaxy.
Yes.
Is there is there a radio jet, or do you have radio images that show a radio jet? And is there any relation of the radio jet with these blue structures that you find?
So unfortunately, it's a bit challenging to say and to detect the presence of radio jets based on our observations. So we have JVLA data for this galaxy, but unfortunately, it's very noisy observation. We can see kind of structures and particular a sort of elongation towards the region where we detect the filament. But also talking with people that have much more experience than me, of course, on the radio side, they were a bit careful to say that indeed we can nicely detect the presence of a jet.
Okay. Can you go now to the BPT diagrams for
Yes.
this BCG galaxy?
Sorry, it's here.
So, okay. So you say that when you go to the blue structures, it is a mixture of star formation and AGN. Now, this liner-like emission can also be due to ionization from very hot stars, old stars. And I think that the discrimination between AGN and this ionization from hot stars is given by the equivalent width of the oxygen-3 line. So have you checked whether there is a variation of the equivalent width of oxygen-3 from going from top to bottom?
Thank you very much for highlighting this. Indeed, we didn't. It's something that we'd like to check. At the time, we didn't look at it. So I cannot really tell you something about the equivalent width of oxygen-3. Yeah, but it's something that maybe...
So if the equivalent width of oxygen-3 is small, it's very small, then it's mostly probably due to stars, to the hot stars, while very high equivalent width is that of AGN. But I mean, just as an indication, it's not necessarily true. So my last question is about the clamps.
Mm-hmm.
You said that they are very short-lived. And can you get any and you said at the beginning that this fate of clamps could have two possibilities. One is that they are ejected from feedback, either stars or AGN, and then or that they could migrate and contribute to the formation of the bulge. Do you have any indication of which of these two scenarios could apply to your data? So, for instance, from the kinematics of the clamps, if you can get some information from the spectroscopy you have, even if it's not as resolved as the HSD data.
One way to look at this, also following literatures, for example, papers by Genzel and collaborators that apply the same kind of procedures for clamps in lower redshift galaxies, is to look, for example, at Barnum lines and these properties to the kinematics in that case. But here the situation is a little bit more complex. The resolution is very low, specifically for symphony observations. So there we have I would say a PSF of about 0.6, 0.7 arc seconds. If we compare them to our observations with HSD, that's 0.13. So it's really, it's hard to say something from this side. Our information is completely blurred away. And also, if we look at the integrated spectrum, that I know it's not really something, but just to give you an idea, still the signal to noise ratio is rather low. And the spectral resolution of symphony, it's not maybe the perfect solution to see small velocity offsets. So, for example, this is the reason why we didn't apply a methodology like the one in Genzel to estimate the mass, the stellar mass, gas mass outflow rate, sorry. Looking at the broad component of H beta line, for example, but directly applying this equation by Pettini, because we have ISM outflows. We do detect them. If we look at the UV absorption lines, we can see that we have outflows, but the entity of this outflow is rather small. So the velocity is rather small. It's of about 200 kilometers per second, while, for example, in papers by Genzel, it's almost 1 order of magnitude higher. So it's completely different relation, and it's challenging with symphony to see these differences.
Okay, thank you.
Thank you.
I would like to make a final comment or questions. So still, I mean, on this particular subject, because there is clearly a very interesting similarity with what happens in star cluster formation every day in the disk of the Milky Way. And of course, the final stability of the system depends on the balance between the efficiency of star formation and the efficiency of gas expulsion. So this 10 to the 8 year that you find is amazingly similar to the typical lifetime of a star cluster which undergoes these phenomena. So it would be really nice to have, for instance, an idea of the velocity dispersion, because the velocity dispersion of the stars, of course, and the typical size will give you an estimate of the crossing time, which can tell you if this, the outcome of this system is something which will be stable or not.
Yeah, in this sense, I've recently applied for JWST time, actually, to have this galaxy observed with NIRSPEC. So we really hope that NIRSPEC observations will allow us to detect the stellar continuum, optical stellar continuum, our galaxy. So to also, let's say, try to give kind of an estimate on this side, to have also a wider sample of emission lines, because Symphony K-band observations, so it's a rather narrow wavelength window, so we can only probe the presence of each beta and the oxygen 3. And for the depth of the observations, well, we cannot really detect anything from the stellar continuum. But yes, so I have applied for JWST time. Let's hope, fingers crossed.
Okay, so Edoardo, as far as I understood, now the commission will leave. We will have an internal, say, meeting. You components of the commission got a message with a separate link. So we meet there and then we come back, okay?
Okay, perfect.
Will give us 10 minutes or so. Okay?
Perfect, thank you.
Ciao, ciao.
Edoardo, scusami,
sì?
ti ho mandato un mail in cui ho bisogno di alcune informazioni per completare il verbale, se mi rispondi.
Ok, perfetto. Allora invio subito. Grazie. La carta d'identità, il numero lo vedete. Ok.
Giovanni, mettimi cost, per favore.
Sì. Gabriele Umbraco, Mohor, make cost. Okay, I think that we are all back, right? Edoardo? Yeah.
Yes, here I am.
Okay, so if everybody is in, Edoardo, dear Edoardo, this committee was very pleased with your presentation and judged excellent the work that you have done in your thesis. So therefore, I have no hesitation to recommend you to the rector of our university to award you the title, the PhD title in astronomy cum laude. Thank you very much.
Thank you so much. Thank you very much.
Applauso.
Congratulations.
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 Davvero bravo, complimenti.
Grazie mille, sono onorato, sono molto contento che diciamo, sia riuscito a trasmettere ecco, un po' questi due progetti.
Senza dubbio, senza dubbio.
Questo lavoro che è stato impegnativo di questi 3 anni, ma che penso abbia portato bei risultati.
Ci fa piacere.
Bene,
Vorrei, se posso,
in
non so se
Olanda.
qualcuno ancora sarà collegato, ma se ci sono anche Giulia Rodigliero, Alberto Franceschini,
sì.
Anita Zanella, Joel Vornè, vorrei ringraziarli tutti per il loro contributo e sostegno.
Ok, ottimo allora. Grazie a tutti, è stato un piacere.
Grazie.
Arrivederci, buona giornata.
Ciao.
Buona giornata.